Lucy, I'll ask you to take it away. Just before you do, I'll say this is our final lecture for today, and hope you've all had a good time learning about the different aspects of AI research. And finally, here to close the day, we're going to be talking about what the state of AI looks like. And Lucy, take it away.
Yeah, thanks so much for introducing, and thanks everyone for coming to the AI Intensive. And without further ado, I'll go ahead and get started. Are you guys able to see my screen here? Okay, perfect. So for the last lecture of today, we're going to talk about state of AI. And to begin with, we will talk about some exciting examples that are in the AI field recently, and then we'll talk about some of the AI research areas, their applications, and with a small deeper dive into the image text models that are most relevant to the AI intensive recently. And then we will talk a little bit about intro to responsible AI. So as AI practitioners, what are some questions that you should bear in mind when you're designing your own models and you're thinking about deploying them? So some learning objectives and outcomes of today is that we'll be more familiar with the accomplishments in AI research, better understand the fields of AI research, more familiar with recent advances in image text models, and the basic questions in responsible AI. Now, let's kick it off with some motivating example. So we used to think that in the fields of creativity, maybe there is a clear advantage from us humans compared to AI. However, recent generative models such as DALL-E and DALL-E 2 has been showing that this might not actually be the case. So for example, here we're seeing an astronaut playing basketball with cats in space, and this is in a watercolor style. And if you actually navigate to their official OpenAI's official website, and there are different things you can play with, such as photorealistic style in the style of Andrew Warhol, or using different entities, different verbs, different styles. These are all amazing things that you can do to generate these very impressive images. And obviously, there are also different tasks that DALL-E is able to do. And there are some like cool demonstration on the website as well, such as generated different variations inspired by the original. So yeah, these are all cool things that generative AI models have been able to do in recent years. And one challenges of these systems is that generating high fidelity and more realistic images and building off those works. So actually Google's more recent work, Imagen, focuses on the photorealism, and it is better at creating higher resolution images than DALL-E 2, according to reported human evaluation. So as we can see here on the left, this is small cactus wearing a straw hat and neon glasses in the Sahara Desert. And on the right, we see a very cute corgi dog riding a bike in Times Square. What's really notable from these work is that these are all very photorealistic and of very high resolution. So as we can see from these examples, the image generated network has really been doing a fantastic job. And yeah, and here just another example, and you can obviously go to Image's website and also look at some other really cool or fun examples as well. So those are on the image front. And on the text front, I'd like to also introduce some other like really cool text model examples that we've seen. So when we think about AI applications, right, we think about, okay, AI can do human task, and then the natural question is that will they be taking over human task? And actually this piece of op-ed is completely generated by a language text model called GPT-3. It is an incredibly powerful language model, and it's capable of doing a lot of tasks, one of them being writing essays that are of decent quality. So for example, this op-ed, it is challenged to compose an essay from scratch to convince humans that AI actually comes bearing no harms to human beings. And here is the first paragraph of that article. And for the later parts of the article, it also leverages a lot of like logical transitions, like inflects, to give examples and illustration for why AI bears no harms. So these are all very cool and very kind of realistic paragraphs that AI have been able to generate. And beyond that, I'm sure many of you may be doing some coding or a lot of coding in your day-to-day work. And then one question you might ask is, well, will they be taking over some of those work? And in fact, these language models are also pivoting towards the direction that they might actually take some of that weight off our shoulders. So for example, here is an example of interpreting the Python program. So the prompt itself is a piece of Python code, and then it's asked to explain what the code does. And the sample's response here, the code above, takes the data frame and a prefix as input and returns the data frame with the prefix removed for the completion column. And of course, this is not limited to one programming language. And SQL, which is used widely in data science and analytics work. I'm sure a lot of data scientists will hope to have some sort of insights and just be validated directly, whether it is supported by data or not. And this is also being accomplished as well. So with the prompt, for example, being that a query to list the names of the departments which employ more than 10 employees in the last 3 months, and the output will be a sample query in SQL that will accomplish the task for us. And in fact, there is a system called Codex that is able to write full programs from beginning to end and of increasing more complexity. So let's take a look at a quick demo. We're not going to look at the full 8 minutes. However, I'd like to just scroll through some of the video to show how it's building up from scratch. So essentially, when humans giving it the natural language instructions, and then it is translated into executable code. And the complexity is just keep on building from having like one object to having backgrounds, different interaction, animation, and interactions between different objects, interactions with the boundary, et cetera, et cetera. So yeah, these are all cool things that current language models are able to accomplish as well. Cool. And then another example that I like to introduce today is GATO. So GATO is a multitask agent designed to solve a variety of tasks. So maybe some of the examples we were discussing earlier, they were just doing one thing. And this is an example of doing different types of tasks, from classifying or annotating images to like even moving the actual arms of robots. And this is the same network that have the same ways to play different games like Atari, using the same ways also to do like chats, stack blocks with real robot arms, and much more, and deciding based on the context whether to input text, join torques, press a button, or other tokens. So this is really amazing how after training, the same set of ways is able to be very versatile in doing all types of different tasks. And these follow images is showing how a pre-trained GATO model with the same ways can do like image captioning, which is the one on top, and also working with like robots and moving, which is one in the bottom. And yeah, these are only some of the tasks that this fantastic model is able to accomplish. And moving on, so beyond these usual, like sort of more close to our daily life tasks, the cool AI tools recently have also been able to advance our scientific understanding and really accelerate scientific discovery. Some of you may have heard about AlphaFold, which is a really important example in AI and life sciences and protein research led by DeepMind. So why do we care about proteins and their structure? Because proteins are building blocks of life, and they underpin every biological processes in every living thing. And because a protein's shape is closely linked with its function, knowing a protein structure can unlock a lot of our understanding of what it does and how it works. So an example of that is understanding the structure of the coronavirus, and understanding its viral proteins enables scientists to understand how it operates and to identify treatments and to develop new vaccines. So the ability to predict a protein's shape computationally, given only its genetic code, instead of having to go through this lengthy and time-consuming experimentation, can really dramatically accelerate research. And this is the goal of AlphaFold. I've also linked here a collab demo. And after this talk, you can also go on to the collab demo to see what are some exact execution that you can do to input the genetic code and then to generate a visualization of what it might look like. And in fact, only a week ago on July the 28th, DeepMind updated their protein database in collaboration with European Bioinformatics Institute. So what happens with this update is that they increase the predicted structure by 200 times, from nearly 1 million structures to over 200 million structures. What that means is that it basically covers structures for nearly all catalog proteins known to science. And this is a huge advancement, and this is showing exactly the power that AI technologies is able to accomplish to help us really, really advance the state of scientific research and how we could accelerate and reduce a lot of time-consuming tasks, given that we have these fantastic models. Okay, so hopefully those are a set of examples that motivates why we are super passionate about AI research nowadays, and what are some research areas that we could look at. Cool. So for the second part of the talk, I like to talk about some example areas of AI research and applications. And specifically, today we're going to do a high-level overview of computer vision, language and speech, recommendation system, and reinforcement learning. So let's get started with computer vision. So for computer vision tasks, at a high level, this line of research is really enabling computers to recognize, understand content, and even generate the content from these images and videos. And if we have to categorize it into different subtasks, different subcategories, it will be image and videos. And in today's overview lecture, I will dive a little bit deeper into the different subtasks within image. So within image, there are also different areas that people focus on tackling. So classification is relatively straightforward. So for example, image recognition can help cars identify objects in their surrounding, can help doctors detect tumors, can help factory managers spot production defects. These are all based on classification. For example, is this a defect or is it not a defect? How do we interpret that? And the second category, which is semantic segmentation, it is the task of assigning individual image pixels a category, such as this pixel belongs to a person, this pixel belongs to a bicycle or background, et cetera, et cetera. And this is exceptionally important in the era of self-driving cars, because this will be really important to annotate in a car's vision, whether this is a pedestrian or whether this is a road, this is a car, etc. And detection, most of us are probably more familiar with face detection. And to make it up to speed with what's happening in the world right now, face detection might encounter a lot of additional challenges because people are now wearing masks. And in fact, a lot of studies have been done on how we're able to adapt these face detection systems, given that people nowadays are all wearing masks. And some interesting findings are facial recognition systems are still performing relatively well on mask faces, although, well, of course, this is not doing as well as the non-mask faces. However, we are seeing the gap being narrowed down since 2019 when COVID first hit. So that is also some really exciting and promising news that we see in the area of detection. And another area is image generation. Probably familiar with the terms like deepfake and generating face images or face videos of celebrities, etc. And here is an example of an evolution of GAN process on face generation. So it is really marvelous to see like how far we have come from 2014, from this very first image to what we have in 2021, which is super, super realistic. Cool. Now that we've touched on a couple of the different tasks that computer vision research is tackling, let's look at some novel applications of CV beyond the scope of like self-driving, face recognition that we are more familiar with nowadays. For example, one way we can employ this is to ensure employee safety in a work environment. So this computer vision system has been deployed in over 10 countries and have been able to detect over 1.8 million unsafe activities in 18 months. So by using computer vision techniques, we're able to highlight by heat maps, what are the more likely areas for incidents to happen, whether our employees are wearing PPE to protect themselves, whether they're doing some dangerous driving acts. So these are all applications of computer vision that can help to ensure that more people are safe, but with less actual human manual supervision. And another pretty cool application of computer vision is in alignment with climate change. So as climate change worsens, the global population might be exposed to more natural disasters and more about maybe like property, maybe life might be threatened by these disasters. So AI augmented systems have also been produced to advance the vision assessment tools. So for example, this is a system that have been developed to allow homeowners to take photos of damage of their home or cars after a natural disaster such as a hurricane, and then to predict the repair costs and to unlock insurance claims and payouts a month faster than if you do not have such a tool. And this is a tool that actually has been employed in Japan last year in forecast of a hurricane incident. Cool. So that is a high-level overview of computer vision, its task, and some of its applications. And the next topic we will talk about is language. And following a similar route, I'll be explaining what are some of the tasks within language and speech research. So to begin with, the first one we'll talk about is language and understanding. So this is just as if when we were going through like secondary school, middle school, education, where we're doing all those like multiple choice questions on understanding and comprehension. For example, in the context of English, English language understanding challenges AI systems to understand it in various contexts, such as sentences understanding, yes, no reading comprehension with logical reasoning, etc. And here's some of other tasks that are really important as well. So for example, speech recognition, most of us are pretty familiar with speech recognition, such as when we're using like Siri or using other systems. However, what makes it challenging is the way people talk really varies, whether it's quickly or slurring words together or with varying emphasis and intonation in different accents. These are all the interesting problems that people in the space are tackling. And then natural language generation or text-to-speech will be a reverse of the first problem. Text summarization is a challenge of synthesizing a piece of text while capturing its core content. So if we have developed AI that are doing really well in text summarization, then this could be beneficial in a variety of areas, such as helping universities classify academic papers, to helping lawyers generate case summaries, etc. And for sentiment analysis, Sentiment analysis is the task using natural language processing techniques to identify sentiments such as very negative, negative, neutral, positive, very positive of a given text. However, interesting problems that will arise there is that when there is a lot of ambiguity in how the question itself was phrased, for example, if I say something like, to say that disliking winter weather is not really my thing is completely inaccurate, then having AI system to tell what is the actual sentiment underlying these sentences with a little bit more ambiguities may be a little challenging. And last but not the least, part of speech tagging, also called grammatical tagging, and what it really tries to accomplish is that identifying the work of different words within a sentence, such as make is a verb and I can make a plane, and it is a noun in what make of a car do you own? Yeah, and let's look at some interesting language applications. So back to Codex, which is a really cool game programming tool that we saw at the beginning of lecture. So Codex is a system trained using large language model GPT-3, in addition to billions of lines of code. So how it works is that after breaking down a problem into manageable, smaller problems, then Codex can map these problems to existing code, whether it be libraries, APIs, functions automatically, and OpenAI's Codex can understand the context of the instructions and also retain memory of previous instructions to give more efficient reasoning over new queries. So yeah, so here is a working example of how Codex is doing an analysis program based on human input. So wait a second, people might be asking then, is it going to take over my job? Is it going to do all my leak code or cracking the code interview for me? So I'll give you like a couple of seconds to think about, okay, so if we give it a like intermediate or difficult level code problem to solve, what is the accuracy? Yeah. Hopefully people have an estimate of what they think it is. But in fact, State of AI research published in last year that the accuracy is well below 5%. So I guess the TLDR from here is like, don't expect programs to do your leak code for you, at least for now. And similar thing happens in competition math, although previous studies have shown that these language models are doing a decent job in composing mathematical proofs, the more theoretical level. However, when it comes to more intellectual and interesting like competition math problems, it is still struggling quite a lot. And another example I want to talk about today is textless NLP. So before we do that, I'd like to also talk about what is some trend that is happening right now. So GPT-3, like we mentioned just now, is a really big language model. In fact, it has billions of parameters, making one of the largest models in the world. And it is now in a scale-out phase, and it's actually becoming more nationalized. So what that means is that different countries is also adapting it to their own languages and to have large language models in their like languages and locales. So for example, the largest Chinese language model, Wu Dao, is also the largest language model in any language. It has 1.75 T parameters, and it is even 10 times the size of GPT-3. However, there is a very important limitation to these sort of like scaling, is that these applications are really restricted to languages with very large text databases suitable for training AI models. Therefore, another recent advancements that's been doing is that, okay, so we want to also develop models for language that might not have as large of a text database. So what if we leverage raw audios directly? And in fact, it can complete audio generation without any labels or text. I've also embedded here a link to listen to some of the textless NLP generation that you guys can check out after the lecture. And just wanted to point out what are some of the benefits of textless NLP. So in short, it should make AI more inclusive and able to model a richer variety of languages than it is possible today. And the majority of textual information available online are just a couple of those languages, and mostly like English, and better use of audio information available online through like podcasts, local radios, social apps, etc., could help improve current AI audio systems performance on the rarer languages. And being able to generate speech only from audio signals in a self-supervised manner could result in more natural and expressive AI systems as well. Awesome. So next AI research area I'd like to talk about is reinforcement learning. So reinforcement learning is a type of learning guided by a specific objective, which is an agent is learning by interacting with an unknown environment, typically in like a trial and error way. This is the common way of learning for a child who does something and observes what happened and take that input in our next step and try things again. So basically in reinforcement learning, what is happening is that an agent receives feedback in terms of whether it's a reward or a punishment from the environment. And then it uses that feedback to train itself, collect experience, and iterate on that experience. And that is a high-level idea of what reinforcement learning is doing. Another relevant characteristic of reinforcement learning problem is that in any situation, the agent has to choose between exploiting the current knowledge of environment or exploring action it has never tried before, meaning that, okay, now I know based on these information, this might be something that is most beneficial, but there are also options that I've never done before. So how do I manage the trade-off between these two? So with these RL research, there are also some really cool applications in academia and in the industry. You may have remembered that a couple of years ago when AlphaGo successfully beats Lee Sedol, one of the greatest Go players in the world who started playing at the age of 5. And since then, the stage of RL has also been advanced to playing like multiple games, defeating people in multiple different games, and even to nowadays to even beating people from not knowing the original set of rules and learning from the environment what the set of rule is. So this is a really exciting trend, how AI system does not even need to be told the rules, thanks to its ability to plan winning strategies in the unknown. And even in more like complicated, like real-time strategy games, recent deployment of AI and reinforcement learning have been showing really amazing result in defeating one of the leading players in these real-life strategy games as well. So for gamers in the room, maybe one day when you're having fun on these platforms, you are interacting with an RL agent also playing against you. And last but not the least, AI, specifically RL, has also been employed in our combat against coronavirus as well. And one of the real-world deployments of AI here is that it can help us choose which population to be tested, especially in the context of border. So the system EVA was developed in Greece, where there was often limited testing capacity at a border. So one solution to that is a robust automated system capable of accurately predicting who should be tested. So given a specified fraction of travelers who could be tested, EVA could select the passengers that really needs to be tested at the border. So these are a couple of exciting applications of the RL area. And one last research area that I would like to touch upon today is recommendation system. And this is something people are probably most familiar with because we are all spending a lot of time on like TikTok and other social medias. So essentially for recommendation system, there are two types of main categories that people are pursuing. So either it is collaborative filtering methods, or it is another content-based methods. So for collaborative filtering methods, they are based solely on the past interactions of recorded between users, items in order to produce recommendation. So a reasonable challenge from there is the cold start problem. And another area of research within recommendation system is the content-based approach, which will take into account different information such as age, sex, job, other personal information as well, to do the recommendation. And application, people are probably already very familiar with how this app has been eating up a lot of our time every single day. So I probably won't elaborate on that. Yeah, so those are an overview, a lot of exciting AI research fields and some of the applications. And moving on to the next part of the lecture today, I will talk a little bit more about progresses in recent year in terms of image text models. So to kick us off, first, an overview of what we'll be covering in this section. So first, we'll begin with a high-level understanding of transformers and attention, which has now become really important building blocks for a lot of these image text models. And then we will look at some contrastive learning methods such as CLIP and some extension of CLIP. And then we are going to talk about some trends in recent image text modelings, and also look at an example of Flamingo, which is combining these directions and trends together. So yeah, what are transformers? Well, these are not the transformers that will be looking at. And from earlier today, you guys are probably familiar with some of the foundations of transformers and how that works in actual code already. But just to reiterate a little bit on a higher level to solidify the understanding. So essentially, the important parts in the transformer building block is the sequence encoding, attention, and self-attention. So for positional encodings, at a high level, what it's accomplishing is that, for example, in a translating use case, instead of looking at words sequentially, you take each word in your sentence together, and before you feed it into a neural network, you slap a number like 1, 2, 3, 4, depending on what number of the words is in the sentence. So in other words, you're storing the information about the word and the data itself, rather than in the structure of the network, which is what recurrent neural network before transformers came into being has mostly been doing. And then as training and work on lots of data, it learns how to interpret those positional encodings. And you will never forget about the word order of the data, which might be a problem in other RNN or more traditional architecture. And for attention, this is a concept that came into being before the transformer itself. So what it does is highlighting what is the most important piece of information in the task. So for example, if we're translating the agreement on the European Economic Area, and when the model trying to translate it to French, and when it outputs the word for European, it is looking at input words European and economic as the most highlighted and most important words. So the type of attention that we're just talking about is important for translation. But if you're trying to understand the underlying meaning of the language, so you can build, if we can understand the underlying meaning of the language, that's where we can build a network that can do a lot of different tasks, not just translation. And that's what's incredible about Transformer, is that they analyze tons of data, and they can do this self-attention, which is building up from an internal representation and understanding of language automatically. So for example, they might learn the words programmers, software engineers, software developers, they're all synonyms, and they may also naturally learn the rules of a grammar and gender as well. So these are some 20,000 feet recap of what transformers are and how they're becoming the new building blocks. And by being the new building blocks, it is actually the case as well. If we look at the number of citations and if we look at the number of models that are following up from the original transformer and how transformer has been adapted to various different purposes as well. And the second model that I would like to cover is CLIP, which is using contrastive learning methods. So essentially what CLIP is doing is that it jointly trains an image encoder and a text encoder to predict the correct pairings. So this illustration is an idea of what it's trying to get at. So it is learning to pair the correct images and text together. And what is cool about CLIP is that it demonstrates a simple pre-training task of predicting which caption goes with which image is a really efficient and scalable way to learn state-of-the-art image representation from scratch. So after pre-training, and natural languages is used to reference, to learn visual concepts or describe new ones, and enabling zero-shot transfer of the model to downstream tasks. So this is able to predict things that may not have appeared in the original training set as well. So this is called contrastive learning in the field of image text modeling. And extending CLIP, there have also been other works. So VLIT is one of the examples where we are able to use arbitrary text inputs in addition to like the baseline inputs to do image detection. So let's look at example here. The base from CLIP might be just toy, and then we wanted to extend to arbitrary text input like a toy duck, a blue toy, a green toy crocodile, etc. And there have been other extensions of CLIP and other models as well. And some of the trends that we are recently seeing in this arena are one, from supervision to self-supervision. So although supervised learning is always one of the core issues of machine learning, the scale of unlabeled data is much larger than manually labeled data. And recently, more and more researchers have noticed that and the importance of large-scale unlabeled data are also really important in extracting information. So self-supervised learning has been proposed to extract such language, to express some such knowledge. So in terms of text and languages, one of the things we can do is that language model might read all of Wikipedia and all the internet and realizes that if we are given a fill in the blank of the something jumped over the fence, dog is more likely to appear than the word car. And through these self-supervised learning, tremendous amounts of unlabeled textual data can be utilized to capture the versatile linguistic knowledge that are behind these large pools of data without labor-intensive workload. And a similar process to this technique is also now being used for computer vision, except that it is replacing learning words with learning the relationship between pixels and images. So as we can see here, this is learning like which pixels in relation to which one, which is the object, which is the background, for example. And the second trend that I like to touch upon is using pre-trained models. So a trend that's happening is that we use pre-trained model as a starting point and just fine-tuning on parameters of these PTMs for specific tasks. So like we mentioned earlier, using these self-supervision, we're able to extract the knowledge that are underlying a lot of these unannotated data. So for example, in the fields of images, there might be a lot of information on ImageNet that could be extracted, and for text from Wikipedia. And for a lot of the text information, we're also to extract those images. And then combining them, we also have the field of vision and language together. So using these as the backbone, we're able to do a lot of downstream tasks with just some fine tunings on parameters in order to adapt it to specific tasks. And Flamingo is an example of combining the two previous things that we were just discussing. One is contrastive learning and one is using pre-trained task. So what Flamingo is essentially at a high level, Flamingo is trying to build a model that can rapidly adapt to various tasks using only a handful of annotated examples, because the problems with common approaches is that fine-tuning can be very resource intensive and zero shot is kind of restricted in output. So the intuition for Flamingo is that it can treat tasks such as captioning or visual question answering, which is like open-ended questions for a visual. So Flamingo is framing all of that as a text prediction model conditioned on the visual input. So what it can do is that it can use some pre-trained models and freeze that, and then with some attention network designs to feed that into a sort of like fill in the blank text input question. And another trend that we're seeing building off these previous things is called prompting. So recently, researchers have also been noticing that we are seeing a shift from pre-train, fine-tune procedure to pre-train, prompt, and predict, which is really relevant for zero-shot learning. And instead of adapting the objective language model via, say, like a textual prompt, we can adapt new tasks to language models. And prompting has been shown to be one of the critical parts of zero or few shots learning. And as zero-shot learning becomes more ubiquitous, effective problem framing is also now shifting to what are the efficient prompts? How do we sort of like engineer the prompt to make it more relevant? So one intuitive way to view this problem is that you can see language model as an instrument. And an instrument can play almost an infinite number of sounds, but only some of them sound good. So the way to get better sounds depends on how you use the instrument or like how you prompt the instrument. So an example of that, if we remember earlier, we were looking at DALL-E and some of the images that DALL-E has been able to generate. And this is a funny example where the prompt itself was a human teaching a robot how to be fair and wanted to be in the cell of a concept art. However, what we actually got was fart, which is definitely not what we were expecting. And this is just an example showing how prompting can be really, really important now that we are working with a lot of these like zero-shot models or generative models. And the prompt engineering challenge is also really important because choosing a bad prompt can result in a massive performance degradation in NLP tasks. So what this graph is showing here is that if we're comparing the worst with the best, which is the red bar with the green bar for larger and larger parameters, larger and larger models, we are seeing pretty consistent drop in the total test accuracy when we're using a very bad prompt compared to when we're using a very good one. And those are the main parts of today where we talk about different exciting examples, different areas of AI research application, as well as some trends. And towards the end of the lecture today, I want to talk a little bit about Intro to Responsible AI. Why is it important? Because when we're doing AI research, we want to also be aware of the downstream implications. And as we are practitioners of AI research or developers of different models, we want to make sure that what we're doing is responsible and we can make a positive impact with our work. So today we'll mostly be covering 3 types of challenges. One is in data sets and biases. And the second is a concept called AI safety. And third, we will talk a little bit about AI ethical issues that are emerging today. So for the first one, data sets and biases. a lot of you might be familiar with in past years, there have been a lot of reports on such as Google Translate not detecting doctors, not associating doctors with women, for example, these type of gender biases. And recently, there've also been found that there is also bias based on religion, especially in the case of generating, given a prompt, for example, given a specific ethnicity group, the text being generated might also be very biased. And these are some examples from like GPT-2 and GPT-3 with the prompts and the model's prediction, which apparently contains bias on racism. And sometimes these could be like corrected because humans are able to identify what is the gap and what is lacking that will make the model lack this type of prediction. However, there's also some conundrum recently where people are not as easy to identify where the problem might be coming from. And recently in 2021, there's also been found something called medical AI racism. So what happens is that, well, computer vision models are trained on a patient's medical imaging data of various modalities, they can accurately and trivially predict their race. Clinicians attempting to do the same cannot. So in some studies, this implies that sometimes systems can potentially cause discriminatory results without the domain experts realizing what is actually going on. What is really worrying from it is that the detection is not due to some trivial proxies, such as like a body habitus or age or other potential imaging confounders, which we could easily calibrate or fix. Sometimes the learned features appear to involve all regions of the image and frequency spectrum, which make the mitigation efforts more challenging. So this is one area of active research of how we are able to reduce these biases and challenges when it is less intuitive or apparent to identify where the problem is coming from. And the second topic is AI alignment. So AI safety, formally, it is defined as the endeavor to ensure that AI is deployed in ways that do not harm humanities. So prominent figures in Oxford and UC Berkeley and many research areas have been working on AI today and the advances in AI system. And they're noticing the fact that not a lot of people are asking this key question of how do we make sure that this will not harm humanity? And the concern has been raised as to, but it's come into particular focus in recent years because the advances in machine learning techniques have given us more concrete understanding of what we can do with AI and what AI can do for and to us. And we're realizing that there's still a lot of things that we don't know at the moment. However, at the same time, like 68% of machine learning researchers surveyed believe that AI research safety should be prioritized more than at the present level. And in fact, only fewer than 100 researchers are working on AI alignment in 7 of the leading AI organizations, and DeepMind being one of those. And last but not the least, we will talk a little bit about the ethical questions that will be arising with the larger scale deployment and advances in AI. So for people familiar with like philosophy or other like ethical discussions, you probably have heard about this trolley problem where you can control this lever to control the trolley to whether go to hit this one person or 5 people. And in the era of self-driving cars, it might also come to the question of if a crash is unavoidable and there are 2 people standing in front of the car, one is an elderly and one is a younger person, then how does the system make that decision? And should they also only be considering that the younger person have a longer life expectancy, but what if this younger person may have a criminal record? How do we balance these 2 areas? And the second is that environmental concerns. So with the scaling of all the AI systems and all the larger and larger models that we're working with, this is taking a lot of resources to train, and and people have been concerned about the carbon footprint of these models. So another ethical question is, how do we reduce the number of carbon emissions, and how do we reduce the carbon footprint, but still maintaining a decent amount, but still maintaining the level of accuracy and AI performance that we want to achieve. And third is wealth distribution. And this can come in a lot of angles, but one of the interesting angle to think about is how these models developed by a small team of people is actually maybe taking the jobs of millions, or significantly challenging or affecting the wealth distribution landscape at the current level. So if we think about GPT-3 that we were talking about earlier today, it is developed by a team of 150 to 200 people. But if we think about the downstream implications of all the things that such a large language model is able to accomplish, this is way beyond the scope of 200 people, and it's even to hundreds of thousands and millions. So how do we think about the distribution, and what is the downstream wealth distribution that will stem from these? So these are all interesting questions that are related to AI research that we should keep in mind. So when we're doing the technical advances, we're also aware of the responsibility that as practitioners we bear on our shoulders. So yeah, these are all I have for today's AI advances and research lecture. Hope you enjoy it, and I will be sharing these slides so you can also click into the different resources I shared to, for example, play with the collabs or listen to some of the examples. Yeah, thank you so much, and thanks so much again for coming to the research intensive. I'll pass it on to Professor Rajpurkar.
Thank you, Lucy. Excuse me, for the wonderful overview of the state of AI.